Hi, this is Peter, and I am doing a demonstration report here for metal powders. The reason we decided to do this presentation was because we can give a demonstration report of some of the additive manufacturing powders that were analyzed here, but there's a lot more information than just what can be given in a report. So when we go through and look at the report, we start looking at some of the comparisons. So there were two stainless steel samples, acero inoxidable, which is stainless steel, cobre, copper, and bronze. There are three samples here. So what we're going to be doing is looking at the individual data runs for the stainless steel. We'll look at copper, we'll look at bronze, and we'll do the comparisons. So the first sample that we have is a stainless steel sample. It's acero inoxidable, and basically it's a stainless steel sample. The data report here shows a few different things that I'd like to bring up. There's a number weighted distribution and there's a volume weighted distribution. The volume weighted distribution is always very useful, especially if you're looking at a result and trying to compare it to, let's say, laser diffraction, which actually generally reports on a volume basis. Keep in mind the Particle Insight is a dynamic image analyzer. It's a number-based instrument, so it gives you individual number data. It captures every particle one at a time, gives you the information and the data, and the histogram is based on number data. So we tend to generally look at a number-weighted distribution, but it's important to look at both. If you notice, when you look at a number-weighted distribution, maybe not in this sample, but in other samples, you can see fine particles. But in when you look at a volume-weighted distribution, the larger particles that by number may not be very many, by volume it makes up a lot of information. So it's always good to look at both number weighted and volume weighted information. Because these are stainless steel additive manufacturing for 3D printing samples, we also looked at circularity, we looked at bounding rectangle aspect ratio in many cases, but ultimately we also look at some of the different thumbnail images. So we also look at some of the correlation plots, and I'm going to go through in the software now and how we go over this. So when we go to the software and we see the data, we have the number weighted distribution again. We can actually look at the large display, and we can look at the volume weighted distribution if we'd like. And remember, because it's a number-based instrument, we can tell you how many particles you had in any area. So for example, if you wanted to see how many particles you had greater than above 70 or approximately 70, there were 21 particles. And we can actually show you those images as well. There's a lot of data that's given, but the true solution of a particle shape analyzer is what you can do with that data. Of course, we can go through and we could look at the different thumbnail images, and we can go through every single one. But that really doesn't offer us a whole lot of information when we look at all the thumbnail images. What we tend to try to do is look at things like, for example, the circularity. Let's look at that again. Look at the circularity. You can see, for example, some of the particles are rough, some are more smooth. We can actually determine and make some kind of a determination as to what the flowability is of these particles. So I would tend to say that if a particle has a if the particle has a greater circularity, so if the particle has a higher circularity, it will flow better, especially in the 3D process. You'll get better spreadability of the particles as well. Another thing you could use circularity for is for reusing and recycling of sample. So for example, let's say you are done with doing a 3D print. There's a lot of excess metal powder that's available. You can actually reuse that metal powder. However, if the metal powder happens to be partially fused, you can actually damage your nozzle. So for example, let's say this particle, if that's partially fused, or if this is a partial fusing, that can actually damage the actual nozzle, and it could actually damage the strength and the integrity of the future parts, the subsequent parts that are made. So particle shape analysis, because it's a number-based instrument, we can tell you what percentage of these snowmen there are, if that's of interest, and that might be important for the spent metal powders. So another tool that we use quite a bit is the Cir Correlation Plot, where we can actually identify in a sea of large particles that how many particles are outliers. So for example, in this case, let's say we did want to look at a used sample, we can actually determine that based on circularity, maybe circularity by size, we can determine that by circularity, if there are some outliers that have a very low circularity, those could be the spent particles that actually may not be good for subsequent use. So we can actually set up a limit, a quality control limit, to look at that. The quality control limit basically are done with a pass-fail criteria. So you can actually tell your operators that once a sample is completed, you can actually have the sample reused only if it has a specific amount of, or not too many of these snowmen or fused particles, and you can set those limits here. So it's very easy to set a set parameter, and your operators can actually retest it before it's reused. So this is one sample of stainless steel. We have another sample of stainless steel that we ran, and it was this, let's see, it was this S2, I think is the one that we're looking at. So this is another sample of stainless steel, slightly different, some more fines. What I like to do when I get samples that are seem to be the same, so there's two samples of stainless steel, I tend to like to compare one to the other, because chances are the customer sent them in and they're interested in comparing one to the other. So we compare that first one that we ran to the second one that we ran, which was S2, and we do an open. We can actually do a comparison and see how the size, the mean size changed. We can actually do an overlay, and we can see that in fact this S2 sample, which is the blue one, definitely had some more fines. On the high end, they were pretty similar as far as size goes. It doesn't go anywhere above, let's say, the 50 to 60 micron range, but there are definitely much more fines than the C2 sample. So the S2 sample had more fines. Let's look and do a comparison, not just on size, but let's look at a shape comparison. So let's see what the circularity differences were from one to the other. So there was a big difference in circularity as well. So in circularity, we can actually see that the second sample, the blue one, the S2 sample, had a higher population of less round particles, less circular particles, one being perfectly round. So it looks like the first sample, C2, has a much more uniform circularity as well. This one's much broader. So I would tend to believe, because of this, that maybe S2 is actually maybe a secondary analysis with some particles that are not only some finer particles, but there are also some particles that are less round. I tend to also look at circularity. I also look at smoothness sometimes to see if the particles are smooth. And again, it looks like there's some more irregularity in the second sample as well compared to the first one. And sometimes what I'll do is, especially for 3D particles, I'll look at an aspect ratio, like a bounding rectangle aspect ratio or Fourier aspect ratio, and I'll do some comparisons there. And here it's kind of more difficult to tell, but we can see that the aspect ratio for the, let's see, for the blue one is lower. Now that's interesting, because that tells me that the aspect ratio for the second one that had lower circularity and lower smoothness has a more uniform aspect ratio, whereas the red one, which is the first one, had a higher aspect ratio. That's interesting. That's an interesting comparison. Well, there's the comparison of the two samples. If we want to go to the second one, which is the S2 that we were looking at, and just look at some of the thumbnails, we could look at some of those thumbnails and see what they look like. And it could be that go through all the different samples. It could be that some of the smaller particles was throwing off some of the circularity values. Well, this is the stainless steel comparisons. Let's go through the copper sample. The copper sample is going to be this one. And when we look at the copper sample, what I found very interesting is that there is a bimodal distribution. So there is one population here, one population here. If I look at it by volume, you don't see it as much, but there is definitely a population difference when you look at a number-weighted distribution. What I'm going to do here is not only just, first I tend to like to look at some of the thumbnails just to see what they look like. And I'll go through and I'll see what some of the thumbnails look like. And there's some pretty irregular sample, some irregular particles, some round ones. What I tend to do as well, I'll look at maybe this correlation plot and I see that there are some particles. The circularity is pretty broad, which I expect because the particles are not very uniform. So the circularity is very broad. So chances are that this particle doesn't flow that well because they're not that round. Let me look at some of the actual histograms of circularity as well. Let me look at all the histograms. So circularity, right? So circularity, because the particles were not very smooth and they weren't very round, that's why we have such a broad circularity value. Smoothness is probably the same. Yep, smoothness is pretty much the same. So this is typical of what you would get when you would get a particle that tends to have, let's move this out of the way, this level of irregularity. So this is very typical. So we could look, so one way of controlling, doing a quality control check on this is looking at some of the smoothness and circularity values and size. I think size would also probably be important as well. This is a copper sample. Let's move on to the next, which is going to be a comparison of 3 bronze samples. So that was an interesting one. So the bronze samples that we're looking at here that were ran, there were 3 bronze samples. There was a bronze sample M. There was a C sample and an M and a C mix. So I can go through and show you just the general thumbnails of what the first bronze sample looks like, and very irregular, which again I would expect that we would get then a broad circularity and broad smoothness as a result. I can go through and I can look at, just open up the C sample. So that would be bronze C. And here I can also do another, before I do that, let's look at some of the histogram information. So this is interesting. So here the circularity is not as broad. Do you see it's a much more narrow, much more round? So it looks like this bronze C sample is not as broad. So it looks to me like they're not going to be as irregular as the bronze M sample. Let's move this out of the way a little bit here. And even though there are some that are irregular, we see a lot more round and smoother particles. So that's why I would suspect that, because I'm seeing a lot more uniformity here in smoothness and in circularity. Let's open up the next one, which was actually a combination of the two, and then let's do some comparisons. So the next one was this one, which is actually a M and C, which was a combination of the two. And we could see here that obviously we have our size, our smoothness, which we see kind of the population of what we saw in the C sample, and then the broadness of the M sample. So I expect that this is a mix, possibly not so much a 50-50 mix, but maybe a little bit more skewed maybe toward the C sample, but we can check that out. Let's just look at the thumbnails and see what they look like. It's probably going to be a mix of both, is what I would suspect. And we can see some of the samples that are more irregular that we saw in the M sample, and we saw some of the round ones from the C sample. So we can actually show that data here. We could also quantify that. What I'd like to do is actually do our own overlay. So I'd like to do a multiple run summary. And what I'm going to try to do is I'm going to try to first do a comparison of the M sample, which was the M number 3, and the comparison of the C sample, which is going to be this one. Then we're going to bring in this overlay in. So looking at the two, if we look at the size information only, ECA diameter by mean, obviously very different. So here we could see a very big difference. So we see that the the number one is the C sample, the red. So the C sample is a different size than the M sample. So this is just size. So if we look at the then the circularity of the two, again, very different. So we're going to see that there is the C sample, which is the red one, is a lot more rounder than the M sample. We kind of noted that when we opened up the individual runs. And I'm going to, let's see, look at that, circularity. Let's look at smoothness. And again, the same thing. So very big difference. So the particles from the C sample, much smoother than the M sample. Let's do something. I'm going to open up, I'm going to close this, and I'm going to do a report, multiple run summary. And I'm going to open up the M sample, the C sample, and I'm going to open up the M and the C sample together, and let's see how how the overlays look. So when we look at the 3 overlay, let's look at the ECA diameter, which is equivalent circular area diameter. This assumes particles are round. Let's look at the mean. So when we look at the comparisons, let's see, the M and the C in this case is the red, the C is the blue, and the M is the green. So basically we're looking at the number one is the combination of the two. So by looking at the combination of the two, it looks like that if the mix was done a 50-50 mix, we may not have a 50-50 mix. It looks like it's reporting on a number basis a little bit more the less round particles, which were the hold on a second, which would have been the M sample, I believe. If we look at it by volume weighted distribution, on a volume weighted distribution, it looks more of a 50-50 mix. Maybe because we're looking at the number weighted distribution, it doesn't look like it's a 50-50 mix. So if we look at the red being the combination, it does spread across both pretty evenly. So that's one difference between looking at information on a volume weighted distribution or on a number weighted distribution. Okay, so on a volume weighted distribution, it does look like it spans across both, so it looks like the mix was 50-50. But on a number weighted distribution, if this mix that was sent in of this M plus C was done by weight, chances are that it's going to skew more on the smaller side, because it's going to take a lot more small particles to make up the equivalent weight of less big particles. So that's why it's important to see a volume weighted distribution and a number weighted distribution. Okay, I hope that helps. Well, let me do one more thing. I'd like to actually open up the M and the C. I was just curious if we open up the M and the C to, I'd like to open up that sample, and I'm just curious if I can actually do some segregating here and look at, let's say, a correlation plot, and maybe by size and circularity, or maybe by size and smoothness. So it looks like this is definitely one population and this is the other. So anyways, I hope this helps. It's a much more detailed view. There's many other things that we can work on. We can work on things like classifications, where we can actually do divisions of one sample that's all combined. But would make this video too long. So I hope this helped. It's a good review of some metal powders, 3 different type of metal powders for 3D printing. Thank you. If you have any questions, please contact us.